let's start it. So, LiteX is an open source project developed by Enjoy Digital, and you can find it under on GitHub under Enjoy Digital and LiteX Hub GitHub repository. So we will have a look on that repo very soon. So Enjoy. So this LiteX tool is by Enjoy Digital. So Enjoy Digital is a France-based s- community. It's a organization which is working on the development of this LiteX tool. So so this organization have been there since last 10 years, and it is based out of France. So they specialize in FPGA consulting and full FPGA based system design with more than 50 clients worldwide. Since they are small company, so they have had to be very innovative in order to design FPGA solutions efficiently. So this is the reason they came up with this LiteX tool. So it is a very innovative way of building your SoCs. So let us move ahead. So so is this LiteX just a theoretical, or have any good products really came out of this tool? So yes, these FPGAs are made with LiteX. So in 2014, a PCI-based software-defined radio board with RTX 7 and AD9361 was made with the help of this SoC builder framework. And then in 2017, PCI SDI capture playback card board was developed with this tool. And in 2018, a more powerful SDR board with RTX 7 and dual 9371 was made. So what is the takeaway is that LiteX have already been successfully used in complex real-world FPGA products. So so when delivering solutions to clients, so Enjoy Digital does not just give hardware, they provide custom hardware, FPGA SoCs, firmwares, drivers for Linux or bare metal, and full documentation. So, and you know how they do it? They do it with this LiteX tool. It is a very efficient tool. Now, the philosophy behind this tool. So, the philosophy of LiteX is about exploration and simplification. So, the word light means simple, small, efficient, and portable. So, LiteX provides infrastructure to create FPGA SoCs using Python, making it much easier to try new ideas and converge towards simple solutions. So, next thing, very important thing, that this is open source. So it is a open source project. So user can build their projects with it, give feedback, and contribute back. So it's a win-win collaboration. Very simple to how open source communities grow. So So FPGA open source tools are becoming very strong nowadays. For example, we have YOSYS for synthesis, NextPNR for place and route, and Vextress 5 is an open source core. So this ecosystem create opportunities in market like cloud, edge, and security. So, but all these tools still need a framework to tie them together efficiently, and that is what LaTeX does. So, so what makes up a FPGA SoC? So, typically you need CPUs. So when you are building a FPGA SoC, what all things you need? So we need CPU, interconnects, communication cores like UART and PCI, storage controllers, debug infrastructure, memories, and even accelerators like crypto or video. So LiteX provides a framework that helps you bring all these together in a single SoC. Yeah. So what differentiate LiteX? So it's pragmatic. So it is created to solve real world project needs, and it's consistent and includes all tools you need. It starts simple and minimal and then extended as needed. And importantly, the LiteX community make it easy to collaborate. The vision is building FPGA SoCs should be easy as assembling Lego bricks. So as you can see here, next, why Python? So LiteX heavily uses Python. So most of the SoC description is written in Python, while only 20% is lower level logic. Why? Because Python is highly productive, object oriented, and has a huge ecosystem of libraries. It also means HDL, scripts, and debug and tooling can all use the same language. That reduce complexity and speed up the explanation. So we just write the description of the SoC with Python and it generates the HDL, and it have in the LiteX environment there are uh, there's Vex-5, all these are Scala based uh, all these processors are written in Scala based, and this tool convert that into Verilog. So all the files are generated in Verilog. Just we have to write the description of our SoC with Python. So how it works and how to install it, I will tell you in live demo. So LiteX supports integration of Verilog, System Verilog, or VHDL cores, so you can reuse IP. So the build process is automated from Python SoC description. It does the HDL generation, it generates the constraint, bit stream, and then SDK. So this make it vendor agnostic while still supporting vendor specific optimizations. So it automates the complete so it the generation flow, the flow of SoC is completely automated with this tool, and portability and scalability. So LaTeX is portable across many FPGA families, from ICE40 to Xilinx UltraScale and Intel boards. It also works with both open source toolchain and vendor tools. So this makes it useful for anything from $5 hobby boards to high-end FPGA prototyping platforms. So base SoC infrastructure. So LaTeX already comes with the base infrastructure. So I think anyone's audio is open. Okay, fine. So have anyone doubts till now? Okay, fine. So uh the base SoC infrastructure we were discussing. So LaTeX already comes with base infrastructure. So AXI interconnect, AXI, Wishbone interconnect, ROM, SRAM, GPIO timers. This means you get a working SoC much faster. So one of LiteX strength is CPU flexibility. You can add a new soft CPU just by writing a wrapper. It supports LM32, OpenRISC, and many RISC-V cores like Vex RISC-V, Nax RISC-V. These can run bare metal software, Python, MicroPython, Zephyr, RTOS, or even Linux. So hard arms. It also supports hard arm CPUs like Sync. If you need more power, you can bridge to a host CPU over PCI, and the best part, switching CPUs is as easy as a single command line option. So, so as I said, explained all these things, like you can choose any FPGA, your CPU you want, like lattice, LM32, OpenRISC, and it supports soft CPUs also, with support for MicroPython, Zephyr, Linux. So LiteX come with the library of reusable cores, for example, Lite DRAM, Lite PCI, and Lite SATA. So kindly please mute. So as I said that LiteX come with open source cores. It comes with reusable cores like LiteX DRAM, LiteX PCI, and LiteX Lite SATA. So these code have been used in real-world projects like Hammer Research and STR test equipment. So these are already used. So this ecosystem also includes support for more than 120 FPGA boards. So you already have a big set of Lego bricks available when you are using this tool. So the motive of this tool is to simplify the SoC development as simple as building your own Lego board, Lego. So, so the debug infrastructure, let us move on to that. So so this tool have provided a very big library of various useful cores like PWM. All these are available. You just have to run this Python file and the Verilog code will be generated. And the debug infrastructure. So LiteX also provides a strong debugging ecosystem, host bridge, so you can control the SoC directly from Python. Lightscope, which is a on-chip logic analyzer, firmware upload over LiteX storm, and GDB over JTAG for supported CPUs like Vextress. This greatly simplify FPGA bring up and debugging. So the future of LiteX, the roadmap includes continuing the simplification, possibly supporting other HTLs like VHDL for avionics certification, improving existing cores and developing new ones, adding support for more FPGA vendors, and involving more contributors, including paid developer. The key message is that the project is alive, growing, and fun to work on. So, so to wrap up, when things become easy with frameworks like LiteX, new innovation and experimentation become possible. We have seen people run LineX2 and other projects on LiteX SoCs. So real question is what you can build when SoC becomes this easy. So let us now explore the GitHub repo of this tool. So, was it a good session up till now? Yeah, we will add the recording in YouTube, which we are recording right now. So your question, how frequently LaTeX is used in industry? I've shown you some real-world FPGA projects done with this LaTeX tool. Well, have you seen that? It. So this is a very less people know about this tool. That is why I kept this session. Actually, these boards are built with, these FPGA systems are built with LiteX only. So this is a credible tool you can use in building very complex SoCs. And what was the motive and why I introduced it to you all? Because this is a very good tool. I have tried building some SoCs with this, and I wanted to introduce to our community because with this, we all will research on this and we all will come up with new ideas on how to use this tool, and we will create a lot of content on internet like how to use this tool. So that was the reason that I kept this meeting. So let us now uh, see the GitHub repo of this tool. So for your information, there is Chipyard also for this automated RISC-V SoC making. And we will cover it in future sessions. So for now, we are more focused on LiteX. So if you want to find this LiteX, just search Enjoy Digital on uh Firefox on your browser. So click on this. So this is the GitHub page of the company which have made that open source tool. So this is LiteX. So you can read it, and I've explained all these things. So it is these are the sponsors of this project. And let us now see the installation process of this tool. So you have to run this commands and it will run successfully. So I will show you the simulation of how it runs. First, you have to enable the Python environment and then it will run. So are you able to see my screen?
Yes, Anushka, it is.
Yeah,
Thank you. Thank you for the initiative, Anushka. Very good.
yeah. So we will be building our single board computer SoC with this tool. So not the complete SoC we will design with this. There are some cores available in this tool, but we will design our own tools, so our own peripherals. So this is just for speeding up our process of building our VyomMedha SoC, as you all know that. So this is the LiteX. So this is my LiteX directory. You will get it when you run these commands. So I'm giving you this repo link. You can try it uh, on your PC also. So this is the LiteX directory. So you can see here there are various CPUs like LM32, Minerva, Nax RISC-V. These are all the CPUs which you can integrate with your design. So wait a minute. Let us enable the RISC-V environment here. The Python environment. and then
నేను వేరే చూసుకుంటున్నా.
okay, so now let us navigate to our project directory. So this is our project directory. There are various projects in this. So this is our design. This is the VyomMedha SoC base design, which we will be developing further to actually build a SoC for a single board computer. And we will get it taped out in India itself. So the complete, so it will be a very good initiative towards Make in India. That is why we started it. So let us navigate to our CD, to our project directory. So this is our project, and let us. So our project is this VyomMedha. So this is our directory, and this is our Python file. So let us explain this, how this code actually works. So here we have imported Mygin. So how you will get it? So first run all these commands. This is the quick start guide given in the repo, and you install these things, and then you will in the main directory you will get a LiteX setup.py. You will have to run that, and then let us see how it runs. Like, well, I will show you how it runs. So let us run the simulation of VEX-RISC-V CPU with the help of LiteX. So this is our VEX-RISC-V CPU. So actually, our it is not connected with the Xilinx, so that is why it is giving this. But our SoC is successfully generated, as you can see here. It is not the SoC, it is just VEX-RISC-V CPU generation. So let it be. I will show you my project, CD project, and so this is the generation of our SoC of this is the basic RISC-V SoC. So this is the program running. So kindly please mute. Okay, so as you can see, it have generated all files needed to deploy this SoC on the FPGA. Right now, actually, this code is made for D0 nano board, but right now I don't have that FPGA board. But I will show you the deploying process on FPGA once I get it. So let's see. So this is the build directory. This is
Anushka, I mean, what configuration for this FPGA board we need for this?
any board. You can, I just talked in the slides, like you can use any, just a hobby-based simple FPGAs, or you can use very high-end FPGA with this tool. I can show
Okay,
you
no.
the directory structure.
Basically, my point is like how, I mean, what configuration, minimum configuration do we need to implement this?
Of the FPGA board.
Yes, yes.
Any board. Like I will tell you, wait a minute. So this is the LiteX directory structure. And this is, wait a minute. So these are the LiteX boards. So these are the platforms. You can see so many platforms. It has so many FPGA boards you can use with that. Wait a minute. You can see in the repo also. They have given support for these FPGAs. So these are the different FPGA platforms you can see. So you can run any FPGAs from Micro Semi, Lattice, Xilinx, Ultra also supported. Even that you have might have seen that ICE 40 FPGAs that are they are very basic FPGAs. So you can
Yes.
run that
Got it.
tool for yes.
Good. Thank you.
Okay. So uh you can develop you will have to write the Python files if you want to uh you can yourself contribute to this projects to this repo if you are finding that there is no support for a particular FPGA you can yourself do your contribution here like here these are Xilinx very high-end FPGAs so they have given us support so you will have to introduce this include this Xilinx board rep file in the base.py which I run just now in the SoC. So this helps in building the SoC, this Python files. If you find you are not having the support for particular FPGA, you can develop such Python file for that and the support will be there.
Okay.
So, like I just not talked, we can use hard CPUs, soft CPUs with this tool. Both are allowed. And if you're finding that there is no particular CPU, like we in India have worked on Shakti CPUs. So we can develop our own support for that code using this open source tool. But for that, we will have to tweak into the files inside these directories, and we can include VEX, that Shakti processor also with this tool. So this is the LiteX uh, directory from where we can build our SoC. It have the cores inside. It have the interconnects. As you can see, it have different interconnects, integrations. These are the different cores, open source cores. So you can develop your own Python file for the code which you want, and it is missing here. So this is the Python files for the designs. Yeah. So this is the CPUs. So these are so many Vextress 5. So we can make our own Shakti based folder here and we can include in that in our projects also. So this is the build directory. So you will have to like if you're using Ultra these are different FPGA directories. So if you are using Ultra, so you will have to import this Ultra, this class, this function Ultra platform into your main design. If you are using Xilinx FPGA, so as you can see here, so this is the Xilinx one. So in this platform.py, this is the Xilinx platform. You will have to import that in the base.py, which I have run just now. You have seen that, yeah. So let us see that also. So this is our projects. This is the project directory, and this is the VyomMedha SoC. So let us understand the working of this code step by step. So first so if you're using Xilinx platform uh, or you can say that lattice platform, just from the build directory, you will have to import the Xilinx folder, and in the platform.py, it will have a specific Python file called platform.py. So you will have to import the platform from there. So here we import Mygen, which is Python library for hardware description. We also import standard module like OS module. And so this is the SoC core directory in this. So it gives the CPU, bus, memory, and SoC skeleton. Here we have the builder. It handles the build process. It generates HTL, headers, and a bit stream. So as I just now talked here, like this is for generating the clock of that Intel board. So I am using uh, as you can, this is the IO description. So this section maps the FPGA pin to logical name. So we declare the 50 Hz input clock on pin R8 here. So as you can see here, so we map 8 LEDs, 4 switches, and 2 buttons. And finally, we map a UART with TX and RX pin. So UART uses subsignals, one for RX and one for TX. So this lets LiteX group multiple pins under a single resource. So now we import the platform. If you are using Xilinx, so add Xilinx here, and every platform will have a different description. Like this is the part number of FPGA DE0. I'm using DE0 Nano board. So this is the part number of that board. So here we define our platform class. It inherits from Ultra platform. So we specify the default clock is clock CLK50 and its period is 20 nanoseconds. So in constructor, we call the parent class passing the FPGA part number and our IO list. And here we add a timing constraint. Here you can see we add a timing constraint for the FPGA for the 50 megahertz clock. This helps Quartus meet the timing constraints, and then we define our SoC. So now we define our SoC. So this class inherits from the SoC core. Here you can see we have imported that. So, uh, so here we initialize the soft core, which is the VexRISC-V, a clock frequency, an identifier string, a 32 KB internal ROM for BIOS, and 16 KB internal RAM for software. So we create a clock reset generator using 50 megahertz board clock. So this ties our external clock into the system. Now next, here we have instantiated what we need we have added the modules which we need in our SoC. So we have added LEDs, switches, buttons. So this is and you can add anything. Like if you want DMA in your SoC, you will have to write the code for that here. Like we have done for LEDs, switches, buttons. And as our SoC will be taped out with 130 nanometer legacy nodes firstly. So for that, Wishbone works properly. So here we can have different Vectris 5 cores like with the uh, like Wishbone and Art and AXI based Vectris 5. We can use both here. So now this is the build section. So finally, here's the entry point. We instantiate our platform. We create our base SoC with the Vectris 5 CPU and peripherals. We call the builder, which generates HTL headers and a bit stream. The build produces a top.sof file, which we can load onto the D0 Nano with Quartus. So presently, I am also exploring this tool, and the reason at some places I am also researching on this tool. I don't know it completely. The reason behind introducing to you all was that we will together research on it and we will create content on this so that uh, more people come to know about this tool and of course, we want to make our VyomMedha SoC that we will get it taped out at Monk 9 So let's see. So this is the build directory. This is the after running the base.py, we have got these uh, files, and we this is a ready to deploy project for our FPGA. So this is our very top file. This is our code which is generated with that Python file. Any questions on this till now? Paul Sherman?
Yes,
Yeah, how did you find the session?
very good, enjoyable. I love the flow in the presentation, Anushka.
Yeah.
I'm typing in a few questions I thought of, and anybody else, raise your hand, open the mic too, just to think about.
So we will further develop our single board computer SoC with this tool. So did you find this tool interesting?
I have one suggestion or challenge to everyone here. My expertise is firmware programming, not building of RTL. You want to hear my challenge?
Yeah.
To anyone or everyone here, take the example that Anushka showed here with LiteX and see if you can build a very simple RV32, RISC-V, 32-bit RISC-V core, basic extensions, IMAC. That's it. No floating point. No F, no D. Just basically IMAC, maybe bit manip if you want. Very simple core with as complete and performant pipeline and CPU as you can, maybe 7-stage out of order core, whatever. Good branch prediction logic with a minimum lean number of peripherals. That is only GPIO, SPI, I2C, and UART. That's it. And debug, JTAG, and all that. No Bluetooth, no Wi-Fi, no USB, no PCI, no DRAM, nothing. Just IRAM and DRAM, embedded SRAM. That's it. And see if you can have a very complete, peripheral, lean, performant, decent SoC.
Yeah.
And whoever can do that with good, lean, few number of peripherals with good core competency and performance with the minimum number of LUTs wins the prize.
Yeah, very nice idea. So, I'll stop the recording. Paul, sir, can you send me the recording?
Yeah, I will. A few questions. I'll just to help other people think of questions, I'll throw out some. One is, dare I bring it up, what is the license model of LiteX? Is it a GPL or BSD? What kind of license model is this?
Wait a minute, let us see. BSD 2 clause. It is shown in the repo.
Yeah, it's in the repo. I know a lot of people kind of like that. You mentioned there's a good community focus. How is the community organized? What type of governance is there? Much like in RISC-V International, part of the Linux Foundation, has a pretty well worked out organization of governance, the steering committees and the technical chairs and the elections that go on democratically. Is there much the same for the LiteX community?
No,
And
actually,
our community or committees, is there a regular meeting, different groups meet regularly to discuss things, or it's pretty much all individual?
so this community, LiteX, is not as big as RISC-V, but it is an active community. I see they are regularly doing improvement in the repo, in the
Just
LiteX repo.
just
Every
through
week.
issues and pull requests and comments in the GitHub repo.
Yeah, actually, we are from India and you are from USA. I think in France they might have a very good community base. In India, very less people know about it. So, yeah,
Um,
this community
I
is
was
growing.
I was wondering, is there a regular chat discussion, or what do you call that? The list serves or other websites that sort of track collaboration together, mailing lists and
LiteX have only a GitHub page right
just
now.
GitHub, and so there's no groups.io kind of
Yeah, they
email
have a
group?
Discord also.
Oh, there's a Discord.
Yeah.
Ah, that's important. You might mention that.
Only 750 members. Actually, this is a very good tool and very less people know about it, uh and they are open to more improvements. Like if we suggest them there's improvement we can do in the tool, so they will accept our
You
ideas.
that's very important, Anushka. You might want to point that out maybe on the first couple slides of to get involved and stay involved. Look at the Discord, and here's the link, and you know the members and
Yeah.
what they're doing. Yeah, that's critical. And how is the LiteX handling for the analog world or mixed signal? Can the SoC be built with a DAC or an A to D, flash A to D or successor approximation or something like that?
I think it
Delta
have
sigma,
only digital
just
codes, no
digital,
analog codes.
no mixed signal, right? Yeah.
But it have a support for micro semi FPGA boards, and micro semi supports mixed signal, I think. Yeah.
And then you mentioned the Python, everything is driven from Python scripts being highly productive. Is there any ability to use like direct command line, bash or shell script calling?
Yeah,
If
there
someone wanted,
is.
you could make a very, very simple, even a makefile based structure.
Actually, we can run a commands also where we can specify what all codes we need in the SoC, and it does the complete flow.
So that,
So
yeah,
actually,
good.
uh, I have also started exploring past few months back. Actually, there's lot to explore more in this tool, and that is the reason I introduced to my community so that we together leverage the uh, this tool to develop some very good SoCs. Yes. Any more question? Paul, are you there?
I was waiting for other people to answer. Yeah, this looks very, very promising and interesting.
Yeah.
For the upcoming RISC-V Summit in October, in the past years, I know there's been the CHIPS Alliance group meeting. I think it's on maybe one or two of the days after the summit. They would meet at the Google Cloud building in Sunnyvale for a day or half a day of good, deep discussion. Seems that something like this could be discussed also.
Yeah. That's a good idea.
Yeah.
So can you save the meeting and send me?
Yeah. Should we stop the recording?
Yeah.
Let's see.